Good day, grade 10s. I want to continue the lesson that we started in class the other day and discuss the types of chemical bonds. It is Unit 5 on page 137 to 150, and it would be good advice to follow is that you can work through those sections in your textbook during this week. So this is video lesson on the 23rd March, covering the topic of chemical bonding. Now, the reason why chemical bonds form is to stabilize the atoms. Now, the first type of bond we started looking at was the covalent bond. They are bonds that are formed between non-metal atoms when there is a sharing of electrons taking place in order to fill the valence energy levels. That would cause the atoms to be stable, like the noble gas atoms. There are very strong electrostatic forces that keeps the atoms together in stable molecules. And these atoms, they bond in fixed ratios. So the molecular formula of a compound would always be the same. It would never change. And we discussed the unique physical and chemical properties of covalently bonded substances in class the other day. We used hydrogen, oxygen, and water. Right, the second type of chemical bond we get is the ionic bond. During the formation of the ionic bond, you have metal atoms joining up to non-metal atoms. And because metal atoms are electropositive and non-metal atoms are electronegative, there's a transfer of electrons taking place from the metal to the non-metal. And the metal forms stable cations while the non-metal forms stable anions. And because there are positive and negative charges, there are strong electrostatic forces between the ions, and they are packed in fixed ratios in what we call crystal lattices. These compounds also have unique physical and chemical properties. The example I'm going to work through is that of sodium. Now, sodium is a highly reactive metal. And it's got a shiny surface. And it's a solid at room temperature. And it's a good conductor of electricity. And the next element that forms part of sodium chloride is chlorine. It's a highly reactive non-metal, and it's a gas at room temperature. So it's not a conductor of heat or electricity at all. It's in fact a good what do you call it? Disinfectant. When these two elements combine, they form sodium chloride. And sodium chloride is a solid crystalline substance with a very high melting point. So the properties of sodium chloride, we actually take it on our food and it won't kill you because it's a toxin. Maybe if you have a problem with hypertension, then sodium chloride could cause your death in the form of a heart attack. Chlorine is so reactive and so toxic. If you breathe chlorine in, you get a sore throat and you can have serious damage to your lungs. Sodium in itself as a metal is so reactive, I wouldn't dare to touch it with my bare hands. So the properties, the unique physical and chemical properties of the compound differs from those of the atoms that form the compound. The next type of bond that I want to look at is the metallic bond. Now these bonds are formed between metal atoms, and the valence electrons are delocalized. It means that the valence electrons are free to move from atom to atom in the crystal lattice. And the reason for that is that most of the valence orbitals are empty. So they overlap to a degree to delocalize the electrons. Once again, because there are positive protons in the nucleus and the negative electrons, there would be strong electrostatic forces between the positive atomic rests and the delocalized electrons. And this causes the atoms to be close packed in lattices. Examples are your copper, your zinc, your iron. Any metal compound has their atoms joined together by very strong electrostatic forces. I want us to look into covalent bonds more deeply in the rest of this video. So just to remind you, there is a sharing of valence electrons that leads to the stable electron configurations. And the strong electrostatic forces of attraction between the nuclei and the shared electrons are so strong that they make the chemical bonds stable. There are different numbers of electrons shared between two atoms. It is possible for two atoms to share 2 electrons. We call that a single covalent bond. When 4 electrons are shared between 2 atoms, we call it a double covalent bond. When 6 electrons are shared, we call it a triple covalent bond. The next property I want to discuss is electronegativity. And the electronegativities of the elements you will find on the periodic table. You've got the atomic number, the relative mass number, and the electronegativity of the element on the periodic table. It's a number that indicates how strong the atom in a molecule will attract the electrons shared in the bond. I'm just going through the theory now, and then I'll use this information in the examples that will follow. When the difference of electronegativity, now the symbol here is that it's a phi, and it's the symbol we use for electronegativity. When the difference in electronegativity is 0, you have a pure covalent bond. And I'll explain it in more detail while using the examples. The next is if the difference in electronegativity is less than 0.9, you have a degree of polarity. In the covalent bond. When the difference in electronegativity is from 0.9 to less than 2.1, you have a polar, sorry, this pen is acting up a bit. You have a polar covalent bond. And the last one is if the difference in electronegativity is 2.1 and greater, then you will have an ionic bond. Sorry, I have not explained this triangle. This triangle here is the symbol we use for difference. So difference in is the triangle we use with the symbol for electronegativity. We're going on to some examples now. So before we go on to some examples, we're going to look at the properties of the covalently bonded substances. Covalently bonded substances have relatively low melting and boiling points compared to the ionic compounds. Exceptions here would be diamond, that's got a melting point of above 3000 degrees Celsius. And graphite as well as silicon are examples there. Then the intermolecular forces between covalently bonded molecules are relatively weak. The nonpolar molecules are not very soluble in water. The polar molecules are very soluble in water. Covalently bonded substances are non-conductors or very weak conductors of electric current. And the reason for that is that the electrons are not free to move through the substance. Now, for the same reason, poor thermal conductors, those electrons, are not free to move through the substance. Most of them are solids, and when they're solids, they are brittle like sulfur. Many of them are liquids, like water, some compounds, including some non-metal oxides, are gases. Another gas would be oxygen, which is an element for that matter, or sulfur dioxide. Right, so these are the properties of the covalently bonded substances that you need to know. Next, I want us to work through some examples. Right, let's choose an example like fluorine. Now fluorine, and I'm going to use Lewis structures to explain the formation of the bond. Fluorine atoms in group 17 has 7 valence electrons. I'm using the crosses, you could use the dots as well. When two fluorine atoms combine to form a chemical bond, the fluorine will share its that one valence electron that is alone with the second fluorine atom. So this, where 2 electrons are shared between the atoms, it is called a single covalent bond. Remember what the other electrons are called, the ones that go together in the orbitals. They are the lone pair electrons. Now I'm going to introduce you to the Cooper structure. Cooper structure, let me use another color here. Cooper structure. In the Cooper structure, we use a dash to represent the bond, the single bond between the fluorine atoms. Next, I want to refer to the difference in electronegativity. Now, fluorine is the element with the highest electronegativity. We'll discuss it in another lesson. It's 4. You find the number on the periodic table. It means that fluorine's got an extremely strong force of electrons shared in a bond. But the second fluorine also has an electronegativity of 4. It means that the difference in the electronegativity, 4 minus 4 is 0. And that implication is that you have a pure covalent bond. And it means that the electrons are shared equally. Between atoms. Right. You're welcome to pause the video anytime you need to think about things. Number 2, I'm going to work through the example hydrogen fluoride. So hydrogen has 1 valence electron and fluorine's got 7 valence electrons. So the Lewis structure for hydrogen fluoride will show that one of the electrons comes from the hydrogen, that shared electron, and another one that forms a bonding pair comes from the fluorine. Right, so that's the Lewis structure. The Cooper structure is H-F. Now, the plot is thickening a little bit. We want to determine whether this is a pure covalent bond or not. So what we do is we calculate the difference in the electronegativity of between the atoms. So fluorine's electronegativity is 4. You always take the bigger number and you subtract the smaller number from it. Hydrogen's electronegativity is 2.1. So the difference is 1.9. What is the meaning of all this? The meaning of this is that it is a polar covalent bond. And what's the meaning of that? It means that the electrons are not shared equally between the atoms. Electrons not shared equally between hydrogen and fluorine. Who's got the stronger pull on the electron? It's the fluorine. Now, another new thing, I can indicate that pull with a little arrow towards the fluorine. Now, when the electron spends more time around the fluorine will think that has got that extra electron and that it is negative, but it's not an ion, an anion. The electron just spends more time with the fluorine than what it spends with the hydrogen. So we say the hydrogen is polarized positively and the fluorine is polarized negatively. There is a charge shift on the molecule that makes it a dipole. Now, the di means two, and pole means there's a positive side to the molecule and a negative side to the molecule. Another thing that we know that has poles is the Earth. It's got a magnetic north pole and a magnetic south pole. So here the idea of the pole is that the one end of the molecule will be positive and the other end will be negative, but they are not ions. It's just the charge shift on the molecule that makes it a dipole. This is a lot to take in, I know that. So please pause, replay, do what you have to comprehend, to make your notes, and to try and understand the work. I want to do a third example. Let's choose oxygen. Now, oxygen's got 6 valence electrons because it is in group 16. When two oxygens get together, then the two oxygens will share these electrons that are alone. And they would share how many electrons? They would share altogether 4 electrons. So this is called a double covalent bond. And in this double bond, you have 4 electrons shared. The Cooper structure for oxygen would show the 4 electrons shared by 2 dashes together like that. To determine the nature of the bond, whenever one atom of an element joins to another atom of the same element, the difference in electronegativity will be 0. So the triangle means difference, and this funny X is a symbol for electronegativity. So 3.5 minus 3.5 is 0. That implies a pure covalent bond. The next example I'd like to discuss is that of nitrogen. Now, nitrogen is an element in group 15, and it's got 1 lone pair and then 3 electrons by itself. So when 2 nitrogen atoms join up to form a chemical bond, then those two atoms would share 6 electrons. Between the 2 atoms. That is an example of a triple covalent bond. And the Cooper structure of the molecule would look like this. There would be 3 dashes between the 2 ends to indicate a triple covalent bond. To determine the nature of the bond, I take the electronegativity of nitrogen, which is 3, and I subtract the electronegativity of nitrogen, and we get 0, and it means that it's a pure covalent bond between the 2 atoms. And that means that electrons are shared equally between the atoms. Electrons are shared equally between atoms. I want to do 2 more examples just to put the cherry on the cake here. Right, example 5. I want us to look at water. Now, water has hydrogen in it with 1 valence electron and oxygen in it with 6 valence electrons. Maybe I should just use dots here with the oxygen so that you can distinguish between the different elements' electrons. So oxygen has 6 valence electrons. When hydrogen joins to oxygen, 1 hydrogen atom can form 1 bond with the oxygen. But oxygen needs 2 bonds, so it grabs another hydrogen and joins to it like that. The Cooper structure for water represents the shared electrons by a dash like this. What is the nature of the chemical bond? We determine the difference in the electronegativity between the oxygen and the hydrogen. So oxygen's electronegativity is 3.5, and hydrogen's electronegativity is 2.1. So the difference in the electronegativity is 1.4. Now that difference is the difference here between that oxygen and hydrogen. So the difference is 1.4 there, and the second bond has its own difference. The difference there would be 1.4. So we don't multiply the 2.1 by 2. The meaning of all this is that oxygen would be polarized negatively, while the hydrogen is polarized positively. So you have a polar covalent bond between hydrogen and oxygen. Now I'm going to introduce the next level here. In English, I'm going to say there is a charge shift on the molecule. The oxygen atom is polarized negatively. The two hydrogen atoms are polarized positively. The molecule is polar. Actually, it's a dipole because the negative oxygen is sticking out and the positive hydrogens are sticking out so they can touch other molecules. And we say in physics, you have an asymmetric charge distribution. That's a lot to take in. The last example in this video is going to be ammonia. Now, ammonia has hydrogen in it and it's got nitrogen in it. So nitrogen's got 5 valence electrons, hydrogen's got 1. So the Lewis structure for ammonia, the hydrogen will share 1 electron with nitrogen, and the nitrogen needs another hydrogen and another hydrogen to share its valence electrons that are not together with other electrons. The Cooper structure for ammonia looks like this. What is the type of bond that we have here? It's a it's a covalent bond. But what is the nature of the bond? To determine the nature of the bond, I need to determine the difference in electronegativity. So for nitrogen, it's 3, and for hydrogen, it's 2.1. To subtract those two, you get 0.9. What does this 0.9 mean? It means that you've got a polar covalent bond here between the hydrogen and the nitrogen. It means that the electrons are not shared equally. The electrons spend more time with the nitrogen than what it spends with the hydrogen. So the hydrogens are polarized positively and the nitrogen is polarized negatively. Now, in the way I did the Cooper structure, you can't see that the nitrogen is sticking out. That's a topic for discussion in another year. But the nitrogen is sticking out as negative and the hydrogens are sticking out as positive. So you've got an asymmetric, sorry for my misspelling there, charge distribution. So the molecule is polar. I think that is enough for this lesson. In the next video, we'll discuss ionic bonds in more detail. Thank you for watching. I hope it helped. Come.